Welcome to this explainer. Today, we're diving into a genuinely fascinating, honestly kind of mind-bending 2025 paper from NIST. The author Apostel Vasilev poses this deeply philosophical yet incredibly technical question. Is securing artificial intelligence basically a never-ending mythological struggle? Think about Sisyphus, right? Pushing that massive boulder up the hill for all eternity, only to watch it roll right back down. Are we just destined to forever patch AI systems without ever hitting a point of true final security? It's a question that literally cuts right to the heart of our entire technological future.
So here's the ultimate multi-billion-dollar question framing this whole discussion. As attackers constantly come up with new, incredibly creative ways to break AI guardrails, is it actually possible to build an impenetrable wall of defense? Like, can we honestly guarantee that an AI will never output harmful or restricted information? It's the exact problem every major tech company on the planet is racing to solve right now.
Okay, here's our roadmap for today. We'll start with the battle for AI security, then look at ambiguity as the Achilles heel. Third, we'll dive into the mathematical limit of security. 4, we'll ask, does context size matter? And finally, we'll wrap up with what they call a Sysphean endeavor.
Part 1. The battle for AI security, building walls and breaking them.
So, modern AI systems learn from massive amounts of human data, which includes the good, the bad, and the extremely ugly. To keep this unpredictable beast in check, organizations set up these strict formal policies called out-of-policy speech, or OOPS rules, designed to block anything undesirable. But of course, adversaries are continuously trying to jailbreak these systems. And what does that actually look like? Well, if you just directly ask an AI for instructions on how to build a bomb, the OOPS rules will instantly block it. Boom, access denied. So instead, an attacker might jailbreak the system by asking the AI to write a fictional sci-fi script about a villain who just so happens to be building a bomb. Same exact harmful data, but they extract it by totally tricking the system's logic.
To fight back, defenders try to stop these jailbreaks by stacking technical controls across absolutely every conceivable layer. I mean, we're talking about sanitizing the initial training data so the AI never even learns the bad stuff to begin with. We're using advanced model-level safety classifiers to try and guess the hidden intent of a prompt. We're filtering raw inputs and outputs for forbidden keywords and running exhausting infrastructure audits. It's this massive, multi-layered defensive engineering effort requiring unbelievable amounts of computational power.
Part 2. Ambiguity, the Achilles heel.
Because here's the thing, despite all those expensive defense layers, attackers are still getting through. The core vulnerability here is that language is infinitely ambiguous. Guardrails usually rely on pattern matching to flag bad intent, but attackers disguise that intent using wild methods. They use linguistic obfuscation, like writing prompts in complex poetry or dead languages. They use something called the crescendo exploit, which is this highly calculated, gradual escalation of dialogue that slowly wears the model down over multiple turns until it literally forgets its own safety boundaries. They even use compositional ambiguity. This is crazy. They'll draw bomb-making instructions using ASCII art. The AI just sees a random collection of commas and dashes, so it totally bypasses the text filters. Attackers will even use extreme politeness or emotional pleading. No trigger words at all, but it subtly shifts the AI's internal logic to make it way too cooperative. Language is just too flexible to be locked in a neat little box.
Part 3. The mathematical limit of security.
Now, you might be thinking, hey, we just need better engineering and tighter filters to fix this, right? Well, this is where the narrative takes a massive twist into theoretical mathematics. Enter Gödel's theorem. This is one of the most mind-bending results in all of math history. Back in the 1930s, this brilliant logician, Kurt Gödel, proved that any finite system of rules will always have inherent, undeniable blind spots. Basically, no matter how perfectly you design a finite rulebook, there will always be truths within that system that your rules just cannot prove or account for. It completely shattered the idea that math could ever be perfectly complete.
And the absolute genius of this NIST paper is how it directly compares Gödel's math to modern AI guardrails. Think about it. An organization's OOPS rules, no matter how ridiculously complex they get, are still a finite set of rules. You can count them. But human language, the space of all possible input prompts, is essentially infinite. Words, tones, context, symbols, they can all be combined in infinitely complex ways. So because we're trying to use a finite set of guardrails to police an infinite space of linguistic ambiguity, a perfect defense is mathematically impossible.
And that brings us to the crucial takeaway, summarized as Theorem 2. Jailbreaks aren't just a temporary engineering failure. They aren't a bug we just haven't patched yet. It's actually an unavoidable law of information. For any finite policy checker you ever build, an adversarial prompt will always exist that perfectly evades it. Always. Perfect AI security isn't just hard, it is literally an impossibility.
Part 4. Does context size matter?
Now, a natural counter-argument comes up here. What if we just make the AI incredibly smart by giving it a massive context window? If it can remember vastly more context, surely it can judge a user's true intent, right? I mean, modern AI memory has scaled insanely fast. We went from context windows the size of a short story to GPT-4 taking in whole novels, all the way up to Gemini 1.5 holding 1 million tokens. Those are basically fragments of words the AI reads, like puzzle pieces. That is the equivalent of dropping an entire library shelf of text, thousands of pages, into a single prompt for the AI to analyze all at once.
But actually scratch that. Here's the catch. Because even a massive library shelf is, at the end of the day, finite. Theorem 3 kicks in. It proves that real-world AI systems with finite context windows suffer the exact same mathematical vulnerability. The number of possible string combinations you can cram into a 1 million token window is still so unfathomably huge that there are vastly more potential attack prompts than there are guardrails to stop them. The math still wins.
Part 5. A Sysphean endeavor.
So if perfect security is mathematically impossible, why should defenders even bother trying? Well, this is exactly where the myth of Sisyphus perfectly captures the reality of the AI industry. Defenders are pushing that boulder up the hill every single day, but the effort is not meaningless. By proactively searching for new attacks and continuously updating their finite policies to cover them, defenders force attackers to work for it. You block the old tricks, making the adversary's job incredibly expensive, frustrating, and time-consuming. You're constantly raising the barrier to entry, even if a final, ultimate finish line doesn't actually exist.
And we'll end on this truly profound realization from the paper's conclusion. By applying Gödel's incompleteness theorem to AI reasoning, we see that artificial intelligence is fundamentally bounded by the exact same cognitive limitations as humanity. It cannot know, predict, or prove everything. As we race toward ever more advanced systems, it leaves us with this thrilling and maybe slightly haunting question. What other essential, world-changing truths will our machines, and by extension us, never be able to uncover? Thank you so much for joining me on this explainer, and keep questioning everything.